Now we're looking at the proof for circle theorem 4. So circle theorem 4 is that the angle in a semicircle is a right angle. So we want to prove that angle ACB equals 90 degrees. We're trying to prove that the angle in a semicircle is a right angle. Now we know that angle AOB, this angle here, equals 180 degrees because it's a straight angle, you know, and also because it's the diameter of the circle. It's the diameter of the circle. So angle AOB is 180 degrees. And we can go back to circle theorem. So if we know that this is 180 degrees, what was circle theorem 3? That the angle at the center is twice the angle at the circumference. Therefore, I can say that angle ACB is 180 divided by 2, which is 90 degrees, because the angle at the center is twice the angle at the circumference. And I can put subtended by the same arc. Subtended by the arc, by the same arc. AB. Okay, but it's enough to say that the angle at the center is twice the angle at the circumference. Okay, but I can also put subtended by the same arc AB. Okay, so if that's 180, then this is 90. Okay, that's the proof for circle theorem 4. Nice, easy one. 5 here, which is angles in the same segment are equal. So we're trying to prove, this is what we're trying to prove, that angle ABC is equal to angle ADC. That's what we're trying to prove. Angles in the same segment are equal, or angles subtended by the same arc are equal. Okay, so what we're going to do in this proof, we're going to join AO and OC. So we're joining those. Now, we know that angle AOC is equal to 2 times angle ABC. Do we agree with that? Or what I could say, I could just let one of them be theta. So I could say, if you want, let angle ABC equal theta, for example. I'm going to let that one be theta. So angle AOC equals 2 times angle ABC, which equals 2 theta. Reason, the angle at the center is twice the angle at the circumference. Angle AOC is 2 theta is because the angle at the center is twice the angle at the circumference subtended by the same arc, and I've got arc AC. Okay, now what do you think I should do? Can I say what angle ADC is as well? Now that I know that angle AOC is 2 theta, so this angle here is 2 theta, what can I now say about angle ADC? Yeah, so angle ADC equals 2 theta divided by 2, which is theta. Reason, and I'm going to put similarly, because it's exactly the same reason as that, because the angle at the center is twice the angle at the circumference subtended by the same arc. So therefore angle AOC, sorry, not AOC, angle ABC is equal to angle ADC. So therefore we've proven, so therefore angles in the same segment are equal, or we've got that alternative wording, which is, so therefore we've just proven that angles in the same segment are equal, or angles at the circumference. So this is actually describing what you see. Angles at the circumference subtended, so we've proven this, subtended by the same arc are equal. Okay, so we've just proven circle theorem number 5. Chording there, but we're trying to prove that a line drawn from a perpendicular line drawn from the center of a circle to a chord bisects the chord. In other words, we're trying to prove that OD bisects AB. okay, or that AD equals DB. We're going to use similar, not similar, but congruent triangles in this proof. So in triangle AOD and triangle BOD, what do we know? OD. So we've got that OD equals OD. I'll just go OD is common. What else do we know? So I'm going to put a dash. What else do we know? We know that OA equals OB equal radii. Okay. Is perpendicular to AB. So angle, I know I've only got one right angle, but there's a right angle on both sides. So angle what? O, I'm doing this triangle. So ODA equals angle ODB. Reason? OD is perpendicular to AB. Equals 90. Yes. Okay, so we've marked in what we know, and it looks like right angle, hypotenuse, and another side. So therefore, triangle AOD is congruent to triangle BOD, and the reason is RHS. So good proof, this one. So therefore, what can I say? That AD equals BD. Corresponding sides of congruent triangles. So therefore, we can write out what theorem 6 is. A line drawn from a line drawn from the center of a circle, a perpendicular line. Drawn from the center of a circle to a chord, bisects the chord. Circle theorem 7 is that equal chords are equidistant from the center of the circle. So given that AB is equal to CD, in other words, that they are equal chords, prove that OE equals OF. So we're trying to prove that those two chords, that AB and CD, which are equal in length, that they are the same distance from the center of the circle. Now, whenever we're talking about distance of a point to a line, it's always the perpendicular distance of a point to a line. Okay, so we're proving that OE equals OF given that AB equals CD. All right. So what we're going to do is we're going to form some triangles. We should prove congruent triangles. Okay, so it doesn't matter which way I do them. I'm just going to go here and here. Okay, so we want to prove that those two triangles are congruent, that OEA is congruent to OFC. We know that AB is equal to CD. That was given because they are equal chords. And we know that that FC is equal to FD, which is a half of CD. We okay with this? Reason? Because a perpendicular line drawn from the center of a circle to a chord, or you just put a perpendicular drawn from center of circle to a chord bisects the chord. So a perpendicular line drawn from the center of a circle to a chord bisects the chord. And we also know that AE equals EB equals half of AB, exactly the same reason, similarly. So now we can say that therefore, now looking in the two triangles, in triangle OEA and triangle OFC, we know that that AE is equal to FC. Reason? It's because the reason is that AE equals half AB, and because FC equals half CD, and because AB equals CD. Okay, that's the reason. But it's all explained up there, so you could just say therefore AE equals FC. But the reason that they're equal is that AB equals CD, and the halves are equal as well. They're two halves, so therefore those two must be equal. So what we've said is that CD equals AB, but these are all halves. That DF equals FC, AE equals EB, but all these four must equal each other because AB and CD were the same length in the first place. All right? So we've got that AE equals FC. What else have we got? We're not allowed to say that OE equals OF. That's what we're trying to prove. What else do we know? Yes, we've got that angle OEA equals angle OFC equals 90 degrees. The reason is that OF is perpendicular to DC and that OE is perpendicular to AB. That's why they're both 90. And what else do we have? So we've got I'll draw the right angles in. What else have we got? We've got no, you can't, that's what we're proving. We're proving that chords that are equal in length are equidistant from the center of the circle. So we're trying to prove that OE equals OF. We know that OA equals OC, equal radii. Yeah, I know that's what you were trying to say. So therefore, the two triangles are congruent. Therefore, triangle OEA is congruent to triangle OFC. And what's the reason? Anyone with the reason? RHS again. Yeah, RHS. Okay, so we've got right angles, we've got the hypotenuse, and we've got another side. So now we can say, therefore, we can say that OE equals OF corresponding sides of congruent triangles. So therefore, what's the rule? Equal chords. Therefore, equal chords are equidistant, are the same distance from the center of a circle. Just put it off a circle.